This is the Puma Plane Wavefront Generator, or PWG, pronounced POOG. It takes an ordinary thermal light source, like a plain LED, and generates a solid parallel beam of illumination from it with a high degree of spatial coherence. It's important to emphasize that this is not a laser. It uses an ordinary thermal light source and so has a very low temporal coherence. See my video on coherence if you're not familiar with this distinction. In this video, I'll show you how to make the POOG and how to use it to demonstrate wave interference using 3D printed Young's slits apparatus. But before we begin, here's a question for you. If I take this POOG saber and point its solid parallel beam directly into the camera with its lens focused at infinity, what do you think you'll see? Well, I'll show you the result later in the video, so stick around to see if you are correct. How can you tell if the rays of EM radiation from a source are parallel? Another way to ask this is, how can you tell if the rays are collimated? Well, from basic high school physics, you'll know that parallel rays will come to a focus in the focal plane of a convex lens. If the rays were diverging, they'd either come to a focus at a plane further away from the focal plane, or never if the rays are too divergent to be focused by this particular lens. Likewise, if the rays were converging, they would come to a focus closer to the lens than its focal plane. So, using this knowledge, we can build a simple collimated ray detector by fixing a projection screen at the focal plane of a convex lens, like this. Now, if any rays coming into the front result in a focused image on the screen, we know the incoming rays must be parallel. Here I have two Puma illuminators, one with the white LED and the other using the blue LED I use for fluorescein fluorescence microscopy. See my video on the Puma LED and lower collector for details of how to make these. Before using our parallel ray detector, let's do a very basic test to see if the illumination beam is parallel by checking the size of the disk of illumination as we move away from the source. You can see that the illumination disk size increases pretty obviously with distance from the white source, so clearly this beam is not parallel but is diverging. Now let's do the same for the blue source. Here, the disk size hardly changes at all with distance, so this suggests that the beam is parallel. So we've found the answer, right? No need to use our more sophisticated collimation detector. Well, let's try it anyway. As expected, with the blue light, we get a focused image of the LED source at the focal plane of the lens, so this confirms that the rays from this source are parallel. No surprise there. Now let's do the same for the white LED source, which gave a diverging beam. But here too we see a well-focused image of the source on the screen, thereby confirming that the light from this source is also collimated into parallel rays. But how can that be, since we already found that the beam was divergent and not parallel? Well, the answer to this is that parallel rays and parallel beams are not the same thing. The beam is just the area of illumination, and this area may or may not be made of collimated rays, even if the beam is divergent or convergent. This diagram explains what's going on with our two sources. You see, the blue LED only has a central tiny emitter spot, so it is an approximate point source of light. All the rays emanate from one tiny spot, so after they leave the collimating lenses, they form only one set of parallel rays, going in one direction, forming a solid parallel rod of light. That's why the beam coming out of the illuminator is also parallel. The white LED, on the other hand, is an extended source. It has a central spot emitter which emits bluish light, like the blue LED, but unlike the blue LED, this central spot is covered by a phosphorescent layer that fluoresces a yellow light over this larger area. It is the combination of this central blue light and this yellow fluorescence that gives this LED its white color, and this also means that the light is emanating from a significantly larger area, the area of the phosphor coating. Each point across this whole area results in a parallel beam of collimated light, but these beams emerge over a range of angles as shown, and so together as a group they form a diverging beam of illumination, even though that beam is composed of a continuum of parallel rays. So, now that you understand the difference between parallel rays and parallel beams, let's examine the parallel beam with the blue LED a little more closely. You see, as I move even further away, the beam does actually diverge a bit. This is because the tiny emitter area in the blue LED is still quite large relative to the wavelength of the light, and also the molded glass lenses used in the lower collector are far from perfect. The Poog is my attempt to improve that setup to make a dedicated high-quality parallel ray illuminator to provide a source of spatially coherent plane wavefront illumination for various imaging applications. From the previous discussion, it is clear that the way to do this is 1. To improve the quality of the point source, and 2. To improve the quality of the collimating lens. As I explained in my video on coherence, the smaller the source, the larger will be the coherence area at any particular distance from the source. Given that none of the available sources here will be a pure dimensionless point emitter but will be partially extended, we would need to go to some distance away from this quasi-point source to ensure a high degree of spatial coherence, according to the Vansittart-Zernike theorem, and so we'd lose a lot of the available light, which won't be much to begin with. So, the collimating lens collects a lot of that light at relatively close range and forces the wavefronts to become flat and parallel. Optically, this places the point source at infinity from the observer, but in a compact instrument with a relatively high intensity output beam. The Poog is designed such that you can use any light source as input, but as this is part of the Puma project, I reuse as many existing modules from the project as possible. The light source is therefore the standard Puma microscope LED illuminator. For the Poog we use the 5mm spacer, and instead of using the full 2 by 23mm lower collector to gather the light, we use the model with only one 23mm lens inserted. I show you how to build this in the first Köhler video at about time point 28:05. The reason for using this single lens modification will become clear shortly. In order to turn any LED into a point source and not just the blue one, and in order to improve light efficiency, this light source is put through a ×40 microscope objective to further collect and concentrate the light into a small spot. I use an RMS standard 160mm tube length objective, and this is why I don't use two lenses in the lower collector, because with two lenses, the output beam which forms the input to the objective is approximately parallel. However, this beam needs to be a little diverging to match the light path expected by a non-infinity objective. This is so that the objective which collects the light will focus it with minimum aberrations at its correct working distance. The coupling of the lower collector to the objective is done using a Poog-specific 3D printed part called the Poog RMS to LC, as shown. In order to connect the rest of the Poog apparatus, you need to screw on a 46mm ferrule to this assembly, like so. Now, the intense focused light coming out of the objective will be concentrated to a point at its working distance, but this point will be the size of a ×40 objective field, which is about 0.5 mm in diameter, and that is still quite large compared to the wavelengths of visible range EM radiation. Furthermore, there'll be diffraction rings around this central spot and other possible artifacts. So, this is not a high-quality point source for generating spatially coherent light. In order to improve it, I then place a pinhole mask apparatus in front of the objective and adjust it to position the pinhole right at the center of this intense point of light, which means it must be at the right distance away from the objective and also centered in X and Y. To achieve all this, I developed these Poog-specific models, and I'll now show you how to assemble them. The pinhole itself is made using one of these two models. The quickest and easiest way to make a pinhole is to print the Poog Pinhole Plane model and simply stick a pin in its central depression to make as small a hole as possible. The smaller the hole, the better quality will the resulting illumination be in terms of spatial coherence and parallelness of the beam. For cases where you need the highest degrees of spatial coherence, you can make an even smaller pinhole, with practice and patience, by folding up some kitchen aluminium foil like so. Then, carefully pressing a thin, sharpened pin into the stack and try not to go all the way through. When you unfold the stack, you'll find holes of various sizes and just pick the smallest one. You then carefully cut it out and glue the aluminium to the Poog pinhole mount model. Using this technique, I managed to make a pinhole of only 30 microns in diameter, shown here. Whichever pinhole you make, you fit and adjust it as follows. Prepare the Poog pinhole mount well model by threading in 3 M3 adjust screws into their holes. But before you do this, you must firmly screw on the Poog pinhole presser model to this end for support. Do not include the pinhole or washer models at this stage. You'll be cutting the threads into the plastic as you insert the M3 thumb screws, so do this slowly and carefully. If you damage the threads, you won't be able to center the pinhole accurately later and the Poog won't work properly. Construction of the M3 thumb screws was covered in my video on the transpolarization illuminator, so see that video if you need more details. Once you've made the threads, partially unscrew the thumb screws so you have some space to sight the pinhole and washer, and then remove the Poog pinhole presser. Now screw this mount well assembly into the 46mm ferrule with the light on, and a piece of paper in the well held down manually either with your fingers or an empty Poog pinhole mount model. The model parts were designed to give an optimum Z position for the pinhole with RMS standard objectives with a 195mm conjugate focal length. So, when it's fully threaded in, you should see the light spot optimally focused on your paper. If this is significantly off focus, you may need to make adjustments to the models or use a different x40 objective. Once you've confirmed the Z position is optimum, remove the paper and remove the Poog pinhole mount well, and grease lightly its base. Also grease both sides of the pinhole mount, only the peripheral parts that will be in contact with the well and washer. Avoid getting any grease near the actual pinhole itself. And grease both sides of the Poog pinhole mount washer model. Then reattach the greased Poog pinhole mount well to the 46mm ferrule. Now insert your actual pinhole with the flat surface facing the objective. Keep the pinhole as centered as possible and put the Poog pinhole mount washer on top of it with its lugs in the gaps for them as shown. Now screw on top of this the Poog pinhole presser until it just holds the pinhole from moving freely, but do not tighten it very much. You want it so that the pinhole can move about in X and Y without too much force, but without being completely loose either. Thread an ARCC lock nut on the other end of the presser module and then screw on another 46mm ferrule. Prepare a convex lens in its holder, as I showed you for making the thin lens of the low power collector or LPC in the first curler video at about time point 2705. This uses the model's LPC lens holder and LPC lens retainer, and the lens has the following characteristics: a 23mm outer diameter, a focal length of 60mm, a center thickness of 4mm, and an edge thickness of 1.3mm. If you can't find that specific lens, then you can use an alternative, but bear in mind you'll need to alter the dimensions of the parts accordingly. Especially note that the distances involved must place the pinhole at the focal length of your collimating lens. Now, screw this LPC collimating lens assembly as far as it will go into the exposed end of the 46mm ferrule with the flatter surface of the lens facing the pinhole. The lens is not perfect, it has a spherical shape, so to minimize spherical aberrations, attach the Poog Front Stop 12 model onto its exposed end as shown. You're now ready to align and adjust the Poog. First we'll center the pinhole in X and Y, and then we'll adjust the front lens to give optimal collimation. It's best to do these adjustments in a dark environment so you can see the beam features more clearly. Hold the Poog steady, here I'm using a mini desktop vise, and take care not to obstruct the 3 adjustment thumb screws. Now, place a movable projector screen in front of it. It helps if your screen has calibration ruler marks on it like this. Switch on the lamp and adjust it to maximum illumination. Now, carefully adjust the 3 adjustment thumb screws till you get the brightest and most symmetrically illuminated beam on your projector screen. This ensures the pinhole is centered. When you achieve the best pattern, fix the pinhole in place by tightening down the Poog pinhole presser. If tightening the presser throws the pinhole out of optimum XY alignment, you'll need to loosen the presser a little, then iterate the procedure till the pinhole stays in its optimal position when the presser is tight. Next, measure the diameter of the beam when the screen is close to the front lens. You can see that here it's about 13mm. And see how or if it changes as you move the screen farther away. You want the beam to stay the same diameter regardless of distance. If the beam diverges or converges, adjust the distance of the front lens from the pinhole by screwing the 46mm ferrule in or out and use the ARCC lock nut to lock it into its final position. You now have an optimally collimated Poog light source, so let's do some experiments with it. Most people who demonstrate Young's slits on the internet do so with a laser of some kind, but Thomas Young had no such device in his day. He used the sun and a pinhole to generate light of high spatial coherence and low temporal coherence. We'll do a similar thing using the Poog, but first we need some slits. To this end, I made some 3D prints which you'll find in the Puma 3D printing guide on the GitHub page. You'll need to print 1 Young's frame model and 2 Young's slit models. You'll also need some blue tack and a sewing pin. Fix the pin in the central groove of the frame like so. It may help to soot the pin first over the candle flame to reduce its reflective, shiny texture, but this is not absolutely necessary. Next, slide in the 2 Young's slits as shown, with the most curved corner faces pointing inwards. Arrange the slits to form 2 thin slots either side of the central pin and as thin and parallel as you can make them, certainly no wider than the pin itself. Putting blue tack on the slits like this helps you to make fine adjustments and keeps the slits in place. Now, stick the whole Young slits assembly on the front of the Poog with blue tack like this. Turn out the room lights. The room must be dark. Turn on the LED and crank it up to maximum brightness. With the projection screen close to the slits, make any final adjustments to the slit pattern to ensure the slits are as thin and symmetrical and parallel as possible. Then slowly move the screen back and by about 50 or 60 centimeters you should see the Young's double slit interference pattern forming, as shown. The pattern will be clearer if you use the blue LED and narrow bandpass filter or some other single color LED, anything but white, and also if you use a smaller pinhole, but the smaller the pinhole, the dimmer will be the projection. The physics of this is well known and I don't want to cover the maths of this pattern in this video, but perhaps I'll do that with a range of diffraction patterns in a separate dedicated video. For now, if you want the details, you can just read up on this in standard physics texts. So now, to answer the question I posed at the beginning, what will you see if this solid parallel beam is directly shone into a camera, or your eye, when your eye is focused at infinity? A solid sheet of light, perhaps? Well, no. The correct answer is, of course, a tiny spot of light, this spot being the image of the pinhole. The reason for this is clear from this diagram. For safety, if you do look directly into a Poog, make sure the LED brightness is turned right down first, and preferably use a neutral density filter over it as well. Even though it's not a laser, that little spot at full intensity could still damage your eyes if you look at it long enough, so don't stare and keep the spot moving around. Of course, you should never look into a Poog that uses a laser source. Now, if some of you thought the answer was a solid sheet of light, it might be because you remember this demonstration I showed you in my first Köhler video with this lens and candle. Here I was demonstrating the Köhler even illumination principle, that a light source in the lower focal plane of a convex lens produces a plane sheet of light corresponding to a parallel beam, just as we have here with the Poog. So, why did you see a plane sheet in that demo and not a spot or focused image of the candle flame? The answer is that the Poog demo and the Köhler demo show the same thing, but from opposite sides of the lens. Before going into that in detail, first let me explain what a conjugate plane is. Two or more planes in any optical system are said to have a conjugate relation to each other in terms of focus if an object or a focused image of that object in one plane is also simultaneously in focus in the other plane or planes. You see, it is true that a solid parallel beam of illumination will look to you like a plain sheet of light, but only if that parallel beam is the beam that is falling on your retina. In other words, the parallel beam is coming out of the back of your eye lens system, not going into the front of it, as was the case with the Poog demo. The reason Köhler illumination coming out of the top of a condenser lens appears as a plain sheet of illumination to your eye is that the other lenses in the microscope create a conjugate focal plane for the focused image of the light source at the front focal plane of your eye. So, the plane of the physical lamp, the lower focal plane of the condenser, the back focal plane of the objective, and the front focal plane of your eyeball all form a set of conjugate planes. This makes your eyeball lens system act like the condenser of the microscope and cause the individual points of the focused image of the lamp to form parallel beams on your retina. And that is why the plane sheet of illumination of the specimen is also seen as a plane sheet of illumination in your eye or your microscope camera. So, when I was doing this demo with the candle and the lens, what was happening is that as I moved the lens closer and closer to the camera, I was projecting an image of the candle closer and closer to the front focal plane of your eyeball, which in my video was represented by the camera, until that image finally coincided with the front focal plane of your eyeball, which is when the image on your retina spread out into an even patch of illumination. For completeness, I should mention that there are actually two separate sets of conjugate focal planes in a microscope that uses Köhler illumination. The first are the conjugate planes of the illumination source, which I just described. These hold a focused image of the light source. The second set of conjugate planes is the set which holds a focused image of the specimen, and this set includes the plane of your retina, which makes sense because that's why you see the focused image of the specimen. One of the clever things about Köhler illumination is that the light from the illumination planes is perfectly out of focus by the time it reaches the specimen planes, assuming you set up your microscope correctly, of course. And that's what gives the images of the focused specimen its evenly illuminated background, even when the light source itself is uneven. In future videos, I'll explain how, using a practical knowledge of these two sets of conjugate planes, Ernst Abbe discovered a better way to explain image formation in the light microscope, which today we call the Abbe diffraction theory of image formation. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.